Okay, this unit is on carboxylic acids, esters, and lipids. The chemistry of lipids involves acids and esters. Now I'm going to go over a little bit on acid. What is an acid? Um, okay, the simplest definition of an acid is a chemical that disassociates a hydrogen cation or proton, sometimes they refer to it as. Um, and so a base is something that receives a proton. I'm going to get into that in Unit 4. Okay, so there are kind of three categories.
Can you move the page back up just briefly?
Yeah. Okay, there are three categories um, of acids. And oops, wait a minute. Okay, strong acids, 100% of the hydrogen ion that's going to disassociate will disassociate. An example of a strong acid would be sulfuric acid, um, hydrochloric acid, nitric acid. Um, and we use sulfuric acid a lot in organic chemistry. But 100% dissociate. So if we were to look at HCl, it would look like that. And that means there is no HCl left. It's only H pluses and Cl minuses, 100%. Now, there are only 7 strong acids in the world, only 7. And these are the 3 most common ones. Sometimes that's called pool acid or muriatic acid, sulfuric acid. It goes by different names. Nitric acid sometimes is called printers acid. And these can come very, very, very concentrated. Like sulfuric acid can be upwards of 17 molar. Very strong acids. I've been burned badly by sulfuric acid when I was in graduate school. Someone, I had a night lab, um, and I was one of the people, washing all the leftover dishes and stuff. And someone had an Erlenmeyer flask full of concentrated sulfuric acid, unlabeled. And I was washing it. I dumped it out and it got on my hands. And then I ended up, burning really badly. So with acids and bases both, you put your hand under cold running water. Well, the water, of course, was hot because I was washing dishes, and so I put my hand under hot water rather than cold water. So it made it worse. So I ended up in the student health center for about 6 hours that night. It was a lovely night, and I had a physics final the next day too. And I ended up burning my right hand, and I'm right-handed, so it was a long explanation. So, okay. All right, so that's strong acids. Most acids are weak acids. Yes, go to the student store to get the lab manual. Just tell them you want it for 306 and they'll go get it for you. Okay, so most of the acids are weak acids. That means less than 99% disassociates. Sometimes it's 1%, it's very little. So most um, of the weak acid is the original acid before it dissociates. Almost all organic acids are weak acids, and there are lots of acids, weak acids in organic chemistry and biochemistry. Tons. Um, things like aspirin, acetic acid, salicylic acid, fatty acids, which we're going to be using today in the lab for making soap. And then there's also another category called a non-acid, and that's where no proton disassociates. Like, for example, ethanol. It's got hydrogens, but none of them dissociate. Okay, and this is all driven by okay, so this is basically driven by how stable the acid is after it loses its hydrogen ion concentration. Now, the fancy name for that is conjugate base. And don't worry about knowing conjugate base. Just know that the stability of the product after the H plus leaves determines how strong the acid is. So in terms of a strong acid, the HCl, SO4, NO3 are very stable. And these are in an aqueous environment as well. Okay. All right. Are there any questions about kind of what is an acid? Well, let me talk a little bit more on. Okay. The strength of an acid is measured by the concentration of the hydrogen ion or proton disassociated. And all of you are familiar with pH. The definition of pH is the hydrogen, the negative logarithm the negative log of the hydrogen ion concentration. Okay, don't worry about knowing about the definition of pH, but that's how the strength of the acid is measured. pH is a number from 0 to 14, and pH can be negative, and pH can go beyond 14, but that's the typical range, 0 to 14. Halfway between 0 and 14 is 7. So pH of 7 is considered neutral. So the county, when it measures the water quality, like coming out of the tap, one of the measurements is pH. And they try to keep the pH above 7 because pH below 7 is considered acidic. And they don't like the tap water to be acidic because if there's any lead pipes still around, and there are, particularly older parts of Sacramento, it will leach out the lead into the water. So they try to keep it like 7.2, 7.1, just barely on the alkaline side. Now, this was the whole problem in Flint, Michigan, when they had those huge water problems, is the water was acidic. And they had a lot of old dilapidated homes that still had lead pipes. And so it got into the water system really, really badly. Okay. All right, so let's go ahead and now and talk about organic acids. Now, we have an organic acid is called a carboxylic acid, and that's because of the weak acid part that forms the acid and releases the H plus. And when you add an alcohol to an acid, you form something called an ester. All right. This is the carboxyl group or the carboxylic acid part. Oops. This guy here. And it's attached to some alkaline group. It could be H, it could be a propyl group over there, 3 carbons, whatever. Doesn't really matter. It's got a carbonyl group, C double bonded O, with a hydroxyl group attached to the same carbon. It's considered a carboxyl group, and it's considered a carboxylic acid. Most of the time it's written like this, not like this. It's probably, and okay, so these are some pretty common um, carboxylic acids. Acetic acid is probably the most common you're familiar with. Also called dilute acetic acid, 5%. 5% commercial vinegar is at 5% acetic acid. So whenever you make it from wine or whatever, usually it's a fruit. Whatever you make it from, they'll then adjust it after the fact to make sure it's at 5%. Now you can buy acetic acid that's more concentrated than that. In fact, the real concentrated acetic acid is called, that's a C, glacial acetic acid. That's 100% acetic acid, no water at all. Propionic acid and butyric acid are frequently used in various household applications, commercial applications. And you've experienced some of this stuff not knowing what you were experiencing. Whenever cream goes bad, there's a particular odor, and that's butyric acid you're smelling. It's a very unpleasant odor. Here they say rancid butter, but usually it's rancid cream that, of course, butter's made from cream, that usually comes from. Um, Blue cheese, Limburger cheese, it's this guy here. It's a 6 carbon acid. Um, you've heard of obviously citric and lactic acid. Oxalic acid is if you're out camping and you've oxtail um, usually grow wild up in the mountains, and if you've ever messed with it, it's very um, coarse. It's almost like gritty, and that's the oxalic acid that makes it that way. Also, when you eat spinach, raw spinach um, versus cooked spinach, cooked spinach is very smooth. Raw spinach has got that slight grit in it, and you're experiencing oxalic acid. And it's basically a double carboxylic acid. Okay, lactic acid is frequently given off when anything spoils. The How you make cheese, for example. When we talk in the next chapter, the next unit, we're going to talk about proteins, and proteins have something called an isoelectric point, and that's the point at which all the groups in the protein are neutral. For milk, casein's isoelectric point is 4. That means when you have bacteria in the milk giving off lactic acid, the pH is going from 7 to 6 to 5, finally to 4. And at that point, all the casein becomes insoluble in water and it clumps out. That's called a curd. And what's left over is called a whey. Okay, the curd is the hard part of cheese. And so if you just leave your milk out, bacteria, usually lactis bacillus, usually starts multiplying and producing lactic acid as a byproduct. And that brings down the pH. When it hits 4, boom, you've got cottage cheese, basically. Okay. Another class of carboxylic acids are called fatty acids. And these are really, really long fatty acids. So they got a carboxylic head, the COOH, and we're going to find carboxylic acids are very, very polar. And then they got this long, non-polar tail. And that's why fatty acids are frequently used to make soap, because once you lose that hydrogen, you have the acid salt, which is called soap. And that's what we're doing today. We're going to take a triglyceride and make soap. So naming acids. Acids are pretty easy. Basically, you replace like propane, longest chain here is 3 carbons long, so it's going to be propane base. And we're going to put a oic acid on there. So propionic acid. If it's got a branch, same thing. You're going to have branch, carbon chain, functional group. Same as what we've been doing. Functional group name is oic acid. We do the backbone, carbon backbone, and then we do any branches. Now, a lot of fatty acids, or not fatty acids, but organic acids, go by common names. Okay, if it's benzoic acid base, that's going to, where the carboxylic group attaches is going to be carbon number 1. It's my dog scratching the rug. That's going to be carbon number 1, and that's going to be benzoic acid. So in this case, for example, we've got 3,4-dimethyl benzoic acid. Okay, so the carboxylate group is very, very polar. It's got hydrogen bonding going on here, dipole, dipole, and usually, sometimes dipole, dipole is here. And of course, LDF. Okay, so they're very soluble in water, up to 7 carbons long. After that, the nonpolar tail takes over. So they become less and less soluble as the tail gets longer. They have high boiling points, greater than alcohols, because their IMFs are greater than alcohols. We will see let's do the graph. That's much more. So you can see here where the carboxylic acids. Now, when we talk about esters, esters are going to fall downwards here, down into here. Once you take away the hydrogen bonding, the OH attached to the carbon, the IMFs go down. But just a plain old carboxylic acid, it's quite polar. So you've got carboxylic acids, alcohols, mainly primary alcohols are very strong, aldehydes, ketones, and then down here we have, and they always forget to put alkenes as well. Because water is very polar with hydrogen bonding, it bonds quite nicely to low, this R group, as long as it's low, they dissolve quite nicely in water. Okay, so here we have that magic 7 carbons long. Once that happens, the carboxylic acid becomes more and more insoluble in water. And that's because that long chain, the nonpolar chain, becomes so strong it overcomes the carboxylic head, polar head. Okay, carboxylic acids, as I was saying earlier, are weak acids. Oops. That means they have low dissociation. So they end up forming the acid salt. And we're going to call this okay. So you need to know this. So in high pH, greater than 7, whatever it is, whether it's an OH group or, let's say it was, excuse me, lye, sodium hydroxide, it's going to take that H off and form the acid salt. And pH less than 7, so this is an alkaline, and this is an acidic environment. In an acidic environment, nothing happens because there's nothing to pull off that H. Here, what pulls it off would be the base. For example, if you had sodium hydroxide, the OH on the sodium hydroxide would react with the H here, forming water. And of course, water is very stable, so that's a very strong driving force for this reaction. Okay, now we're going to see the same setup with bases in Unit 4. What are bases in an alkaline environment? What are bases in an acidic environment? Okay, I just mentioned that. Okay. Now what's going on here, again, is the OH pulls off the H to form water. Benzoic acid, same thing. It's carboxylic acid. The OH reacts with the H to form water. Okay, so to name a salt, to name the salt, we have to name this cation here. In this case, it's sodium. And then we are going to call, instead of we substitute the oic acid part with that. So this is sodium benzoate. Very common preservative, by the way. You'll see that all over the place. So sodium benzoate, sodium, like for example, if we had this would be propanoic acid, and we decided to throw some lye in there, sodium hydroxide, we end up with the acid salt. And this would be sodium. Propanoate. Okay. Okay. The salts are sometimes called soap, depending on how long the nonpolar chain is. The salts are usually soluble in water because of one, they're ionic, so they have a lot of very strong IMFs. And again, the driving force is a C7. Okay, excuse me. The sodium salts are used a lot in for everything, in foods, preservatives, soaps, surfactants, They're just used a lot. Uh, they're used as buffering, for example, citric acid. Um, for example, in cheese. Cheese can melt or won't melt very easily. The more melty the cheese is, it has sodium citrate in it. Sodium citrate will make the cheese melty, gooey. So, for example, American cheese has a lot of sodium citrate in it. So, if you want to have a cheese melty, for example, oh, I don't know, some really aged Parmesan cheese, for example. Parmesan cheese doesn't melt very easily. If you add some powdered sodium citrate to it, it becomes very melty. It's almost like American cheese that tastes like Parmesan cheese then. So this stuff is used a lot, the sodium salts and potassium salts of fatty acids. Now, esters. Esters are formed when we have a um, alcohol and an acid together. Now, in the unit 2, we talked about aldehydes and alcohols and ketones and alcohols. Well, when you have an acid and an alcohol, you form an ester. They are very common in biomolecules. You'll see them all over the place. They're used as flavoring agents. You'll see the artificial strawberry flavor, artificial whatever flavor. Frequently, it's a combination of esters. Um, Esters. I wish we had an when I taught this class up in Tacoma, we had a lab where we made esters, and we turned butyric acid, which smells awful, into the most pleasant smelling menthol, strawberry smells. It was really cool. Um, but we don't have a lab with down at Tacoma. I mean down here in Sacramento. Anyway, the esters are really nice smelling. They're really, really cool. They also are in flavors as well. Okay, so esterification is a process of making an ester. Um, so we've got acid group here and the alcohol group here. And under heat, now this is a double reaction depending on the pH. With heat in an acidic environment, what happens is the H from the alcohol binds with the OH from the acid forming water. And this can be phenol, an aliphatic alcohol. Remember, phenol is this guy here. So that forms esters quite nicely with any kind of an acid. Okay, and then under alkaline conditions, this ester will be broken up back to its original acid, salt, because it's alkaline, and the original alcohol. And this is the basis of making lye soap, this reaction right here. Okay, so if we look at let's see, this is let's look at an example here. So let's take an acid. Let's take butanoic acid. plus ethanol. So we have a primary backbone, and then we have a secondary backbone. So we start with the primary backbone here. And then the alcohol is our secondary. Bond. So this would be ethyl, ethyl butanate, butanoate. I'm going to stress the O8. So that would be a typical ester reaction. Now, there are three ways to make esters. First way is the way I just showed you. And this would be ethyl propanoate. Okay, so we have the acid, the alcohol, acidic conditions under heat, we end up with the ester. Now, the important thing here is this is the poorest way to make an ester. Okay, method number 2 is to take the, this is called the acid chloride. Take the acid chloride, let's back up here a second. Okay, primary backbone, secondary backbone. So we take the primary backbone acid chloride along with the secondary backbone from the alcohol, and then we form the ester. So this up here is going to give us water. This gives us some kind of an acid based on what kind of acid chloride we use. Now, this gets the highest yield. And lastly, we have one that's kind of a medium yield. Now we're going to use something called the anhydride. And what an anhydride is, think of it as a double ester. As if we look at this here as an ester, and we look at this as an ester. So two esters kind of coupled to the one oxygen atom there. So this would be our secondary backbone here in pink or purple. And we'd end up again with the our ethyl propanoate. Now this is the most common way of making esters, is this third method here. And this is the method we're going to use when we make our aspirin. Aspirin is a ester. It's also an acid. It's a combination of an acid and an ester. Okay, so these you need to know. Because I will definitely ask you on the test to show 3 ways of making this ester. Okay, so these are just some more examples. We have the acid chloride, alcohol gives us the ester, ethyl acetate, or ethyl ethanoate. This is here's the anhydride method. So we have the anhydride plus the alcohol gives us the ester, plus it kicks off the other side of the ester into an acid. And this one here, the other side of the ester forms a acid based on whatever acid chloride you started with. And we're not doing polymers that are non-biological, since this is an allied health class. So esters are commonly used to make things like plastics and nylon and all kinds of stuff. But anyway, we're not focusing on those at all. Okay, naming esters. There are 2 parts to naming the ester. The alcohol part we name first, just like we did the acid salt. We named the the cation part of the acid salt first, and then we named the rest of it, which is the original acid part. So it's alcohol part, then the acid name from which it was come from. So for example, okay, this started off as a methyl alcohol. So it's going to be methyl. And this started off as a 2-carbon acid. So that's going to be ethanoate, methyl ethanoate. So the O8 part is similar to the acid salt naming. Now, if you're starting off with phenol, this is going to be treated like a branch. So it's not going to be a benzo name, it's going to be a phenol name. So since it started off with a phenol as the alcohol and benzoic butyric acid as the acid part. We're going to name this phenylbutanoate. Now here we start off with benzoic acid. So that benzo part is going to be kept in the name. Here's the alcohol part, ethanol, benzoic acid, ends up with ethyl benzoate. Now, as I said before, this reaction is and go frontwards and backwards. So basically, we can take the ester apart in both acidic and alkaline conditions, and then we can reform it as well. So what we want to do when we want to make soap, we want to end up with the acid salt of the fatty acid. So that's why we use an alkaline condition to do that with. Hence the term lye soap, which we're going to be doing this week. So basically, we split that ester right at that oxygen there. So this side is the alcohol, this is the acid side. Or the acid salt if it's alkaline conditions. For example, we have ethyl benzoate, okay? So benzoic acid, ethanol. So we have ethanol, benzoic acid. If it's an if it's an alkaline condition, the term is called saponification. So if you have an ester, in alkaline or basic conditions, what's going to happen is we're going to form the acid salt in the alcohol. So again, this is the alcohol part. Oops. And this is the acid part. But it's going to end up being the acid salt because it's alkaline conditions. So here we have methyl benzoate. It's supposed to be ALC. So we're going to end up forming methyl alcohol or methanol. And the original acid was benzoic acid, but we have to name it as sodium benzoate. We have to use the acid salt naming convention. Okay. These are the reactions, and I've combined those into a unit 1, 2, and 3 flow chart as well. So here we have an ester under basic conditions, so that's saponification. Under acidic conditions, we end up generating the acid and alcohol back. An acid plus an alcohol give us an ester, and a carboxylic acid and water will dissociate. If it's in a base, it forms the salt. Now, there are two ways to describe a fatty acid. Actually, let me rephrase that. Three ways. There's omega, and you've all heard of omega-3 fatty acids as being super healthy, omega-6, omega-9, etc. That's one way. It's the least descriptive way, however, of describing a fatty acid. The IUPAC way is accurate, and the delta method is also accurate. So, oh, and then there's the common name too, which I guess there are four ways. You count the common name. Common name tells the least about the acid. The delta and IUPAC are the most accurate. Okay, so nutritionists frequently use the omega way of naming stuff, and it counts from the end until you reach the first double bond. So, for example, this would be an omega 1, 2, 3, 4, 5, 6, 7, 8, 9. So this fatty acid here is going to be an omega 9 fatty acid. The delta way counts the first carbon of the double bond from the acid end. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9. By the way, this is oleic acid. Okay. Okay, the delta has a number of parts to it. Okay. One is the backbone length. Okay, in this case, the oleic acid is 18 carbons long. Excuse me, it has one double bond at position 9 from the acid end. And then we have the IUPAC way. Okay, this is going to be an octadecanoic. And this would be at position 9. And it would be 9. So this is what biochemists and chemists use. Now, this is optional, the mono. You could say 9-octadecanoic acid. Probably it's more common to just leave off the mono, but because we're going to see in a minute, we're going to have di and tri octadecanoic acids as well. Okay, so four ways. IUPAC method, the delta method, the omega method, common name. And these are the acids I want you to know. Now, you're going to, of course, you have your 3x5 card. That would be good to have this on your 3x5 card. Okay, and then lastly, we can form inorganic esters. And these are, with the phosphate ester, are very, very common biochemically. For example, ATP, adenosine triphosphate. Phosphates are esters. And the adenine has got an alcohol group on it, and that's what forms the phosphoric esters. And then we form ADP, adenine phosphate. That's where one of the phosphate alcohols comes off whenever we need to gain energy in a reaction. And that's why we can have adenosine monophosphate, diphosphate, and triphosphate, or AMP, ADP, or ATP. Okay, this is the first step of glycolysis. When we talk about metabolism of carbohydrates, we're talking about metabolism of glucose. So the first thing the glucose does is it gets esterified on carbon number 6, right there. Speaking of ADP, this is what it looks like. So this sugar here is a ribose sugar. And this is all done on carbon number 6. And this attaches to a heterocyclic molecule. So is this a reducing sugar? This would be an easy test question. So what is a reducing sugar? You have to have a semi-acetal. Are there any semi-acetals present in this molecule? So this is not a reducing sugar. Okay, so let's see here. So this is what ATP looks like. Same basic as ADP. We have 2 of them. ATP, we have 3 of them. Okay. So that is carboxylic acid and esters. I know you've been focusing on test number 2, so you probably haven't given this a second thought. But anyway, are there any questions about this guy? What I do for practice on these naming is take this guy, just the structure, and start naming the structure. Okay, so the first part is the common name, oleic acid. Sometimes it's given a shorthand, depending on what literature or textbook you're looking at. Here's the delta version, the omega version, and the IUPAC version. These guys are frequently, you never hear pentanoic acid. You always hear EPA or DHA or ARA. Rarely do you hear the full name. But they are all, these two are omega-3s. Frequently when you buy a tablet of fish oil, they'll give you actually how much DHA and how much EPA is in there. Usually ALA as well. But this would be good practice for naming it. Okay, so These are the reactions of Unit 3. And this is all of them put together. Okay, so you guys have been a ball of questions today. All right, anything else? Um, we'll be making our soap today and Wednesday, and we'll be using our citrus oil that we distilled last week. And I'm gonna have molds for you, different shapes. So we're not using the lab had said to bring a quart container. We're not going to be using that. We're going to be pouring it into molds instead, which are much better looking than so you don't have to worry about that. So just come and with your pre-lab obviously done and all that stuff. And now this is an important one on first aid because you've got um, sodium hydroxide, that lye, and that lye is very caustic. So what happens with lye on flesh, it saponifies the oils in your flesh, and basically it dissolves your flesh. It works quite nicely that way. So you don't want to get that on you. If you do, you need to know what to do. Basically, put your hand under cold water, running water, and you'll be fine. Okay. If there aren't any questions, I'm going to end this. And I'll see Monday, folks, later.